expended. Okay, so I just want to review what we said last time, or what I said last time, right, which was on Monday, which is quite some time ago. So remember, I told you about these maps from the circle to the circle. I called them pi 1. Everybody else would call them pi 1 also, right? And maps from the sphere to the sphere. And somebody said to me, who cares? Why are you telling me all this abstract stuff? And the answer is, I'm telling you this because what I showed you really is that if you give me one map from the sphere to the sphere, or one of these maps, and I said these were all labeled by integers, the degree of the map, then if you tell me you have a degree 3 map and I have a degree 3 map, I know I can smoothly go from one to the other. The whole beauty of doing this algebraically and classifying the maps this way is I don't have to show you how to get from one to the other. It is enough to say I know that they are in the same class and I can smoothly go from one to the other. And that's the great power of using homotopy theory to study these things. And so I could say, perhaps, I can't answer the question, could I cook up a certain dynamics, right, that leads to a transition from one degree to the other. But I could say if you give me a degree 3 initial condition and I give you another degree 3 initial condition, and we're eventually going to go relax to the same, we're doing some relaxation energy method, right, to get to some ground state, we will get the same ground states because one and the other are actually continuously related. Right? I might not have the same path to the ground state, but I'll get to the same place. So that's why it's powerful. So, does anyone remember this talk on Monday? Who remembers Monday? Raise your hand. Okay. Who remembers what they had for breakfast this morning? Well, wait. I said white shirt. I don't know your name, but you raised your hand and then put it down. Do you not remember what you had for breakfast? Well, honestly, I was intimidated by the fact that you didn't know. Exactly. Exactly. Okay. So, so I talked about this thing. I think I called it the ground state manifold. I guess I'm not sure I completely defined it, but for say the XY model, which is basically an angle, or it's a two-dimensional unit vector, the ground state manifold is the circle, S1, right? The vector points anywhere on a circle. And what do I mean by why do I have ground state there? Ground state because any ground state, the point of spontaneously broken symmetries is that if you tell me here's my state and I'm in the ordered phase of the XY model, then all the spins point the same way. But the spins don't know my coordinate system, right? They don't have ears or eyes, so they don't know. So if I rotate, then that's a perfectly other acceptably good ground state. So there's a whole set of ground states that are all energetically equivalent, and so this is the manifold of ground states. What about the Heisenberg model? Heisenberg model, right? Those are 3D spins, okay? And then the ground state manifold is S2, the 2-sphere, because the unit vectors can point anywhere in the 2-sphere. What about liquid crystals, right? Pneumatics. Pneumatic liquid crystals. Well, we already said what a pneumatic is. You have a vector, right? It's a unit vector. It lives in R3. But n and minus n are equivalent. Remember I showed you those Schlieren textures, and I showed you that n and minus n are equivalent. That's why you could have places where you only had 2 brushes coming out of a point. And so what you do here, so if I just gave you the beginning, that's the same as the Heisenberg model. So that's a sphere, like so. But this extra condition tells me that I identify antipodal points. So these points are identified. And that manifold has a name. This thing is called RP2. It's fancy. You start feeling like a mathematician when you have to use bold symbols, right? Blackboard bold. This R, this means real. This means projective. This means 2, right? And what does it really mean? This is the set of all planes in 3 dimensions. Right? See, when I tell you that I only am giving you the information, here's a plane, here's another plane, all the planes that go through the origin are labeled by RP2. Okay? And that's why I don't care about n and minus n. It's the same plane if I turn it. Everyone okay with that? Yes? No? You got to talk. Nothing? Do you have a question? No. I can't tell. You know, in the US, I can read facial expressions of, I don't know what you're talking about, but it's that cross-cultural thing that makes it difficult. And then I could talk about crystals. Okay? And what does a crystal have to do with a topological defect? Right? Well, a crystal, remember what a crystal is. Here's a picture of a crystal. You ready? Okay. A crystal is a bunch of points. Here's a one-dimensional crystal. All right? But your imagination lets you go to other dimensions. Right? It's a one-dimensional crystal. You have this period A, this spacing between points A. And you can say, what's the ground state manifold? Well, you know, I can take the whole crystal and slide it over. I can slide it. And if I slide the crystal by, say, A on 4, this is the A on 4 crystal. So I've shifted everything over by a quarter of a lattice spacing. So I shift by A on 4. It's the same crystal. Just like the XY model doesn't know which way I'm measuring from, where my coordinate axes are, nor does the crystal know where my origin is on the real line. So these two crystals are identical. So there's a whole manifold of ground states. And of course, if I shift by A, I get back to exactly the same structure. So really, a crystal also has, as its ground state manifold, S1. That's a one-dimensional crystal. A two-dimensional crystal has two reciprocal lattice vectors, two directions. You can imagine the simplest case, it's a square lattice, so I can make shifts in the x direction, shifts in the y direction, and they're independent, and I can shift up to one lattice spacing. And so what this just becomes is S1 to the d, where d is the dimensionality of the crystal. So let me try to make this a little more precise, because it has been my experience that not everybody sees it this way. So how would you describe a crystal? This is one way of describing the crystal. And then you might ask yourself, how do I describe deformations of the crystal? Right? And what you say is, oh, I know what to do. I'll just label each point, and I'll tell you how much it moves. And you can do that, and that's a perfectly acceptable way of modeling a crystal, and you know, many people do it that way. But I'm going to tell you a slightly different way. Right? So I'm going to imagine that I have a density of stuff. Density of stuff. That's a bad word, because if I abbreviated it, you might think I mean density of states. So I'll say density of matter. How's that? Okay? So I have some density of matter, and that density of matter can be expanded in a Fourier series. Right? And there's the first term in the Fourier series, which is a constant. If that were the density, what would you call that? I'm going to start calling on people randomly. Because I don't know your names, because you're not, I don't have a roster at this point. What would you call that? Sorry?
Constant density?
Constant density. So is that a crystal? What would you call it?
Say, tell me.
What's a crystal at constant density? Is that a crystal? No, it's a liquid. Right? A constant density means you have a fluid. Right? So this, when I only have the first term, the constant part, that's just the fluid. How do I get a crystal out of it? Well, now what I do is I start writing down the other Fourier modes. And I label the Fourier modes by the reciprocal lattice vectors. For 1D crystal, there isn't much to it. There's some integer m. M goes from minus infinity to infinity, like so. What is m? And then I have e. I have some coefficient rho m, right? M not 0, because I already took count of it here, right? Rho m e to the I 2 pi m x on a, where a is the spacing. Isn't that cool? This is automatically periodic, right? And when I have a crystal, it means that one of these Fourier modes is not 0. One of the interesting Fourier modes is not 0. Agreed? And of course, if you tell me that at the transition, rho 2 is the first one to not be 0, so obviously I'm thinking rho 1 is the first one not to be 0. But suppose you told me that you go to a transition from the liquid to the crystal, and at that point, Rho 2 takes on some non-zero value. See, it's an order parameter. Takes on some non-zero value. Then, of course, the crystal I started with was not this crystal. It was a different crystal. It was one with a reciprocal lattice vector that was twice as big. Right? So I'd say, oh, that was the wrong one. I should have expanded in a different set of reciprocal lattice vectors. Okay. So these are the order parameters. And if I'm near the transition, then what has to happen? Then it's probably enough to write rho of x is rho 0 plus rho 1 e to the I 2 pi x on a, like so, plus the complex conjugate, all right, to make it real. And of course, I can generalize this to any dimension. By writing rho of x is rho 0 plus the sum over the reciprocal lattice vectors, rho g e to the I g dot x. And that's it, right? These are the things that give me the density waves, and they have to have a magnitude. If I don't have the magnitude, remember that whole Bragg thing with crystals? The Bragg crystals made of all these Bragg planes. Those are the Bragg planes, and the rho g's are the amplitudes. Okay? Yes?
Is there any deeper reason that you should assume that there's only going to be one Fourier mode that is important here, the transition? I mean, it can't be two at the same time.
Well, it could be two. That would be, you'd have to tune things through that. I'd have to go diverge or digress into the whole Landau theory of critical points, right? To tell you that, well, generically, I only expect one thing to go through 0 to change sign. Right? Generically, I expect only one mode to go non-zero. Right? By tuning things exactly, very carefully, I can have some kind of exotic crystal or exotic liquid crystal phase, or, you know, you all remember the Ising model. There's the regular critical point, there's the bicritical and the tricritical points. Those are adjusted and found by adjusting more parameters. So it's possible to have more than one order parameter go non-zero at the same time, but I'd have to tune things to do that. Okay? Everyone's with me? Okay. And so this would be the crystal. I already said that. And now I can ask myself, how would I consider changes in the crystal? And how do I even talk about topological defects in the crystal? So the way that I am going to do things, instead of thinking about displacing the locations, I'm not going to think of this as the object I'm changing. These are the Fourier modes. Instead, I'm going to elevate rho g to a function. I mean, of course, even a constant is a function. So to an interesting function, or to a non-constant function. And that means that rho g has a magnitude. The magnitude, of course, are the order parameters. And it has a phase, and I'll just write the phase like this. And u is some new field, like so. So I have the phase variable, and I have this. And you notice that if u were to change by a constant, what happens to the crystal? Anybody?
Translate.
It's just a translation. U changing by a constant is a translation. And if u is a function, it's just moving where the peaks in the Bragg where the Bragg peaks sit. So this is just another way of describing it. And it's a way of describing it that's Eulerian instead of Lagrangian, because I'm writing everything in terms of functions of where I am, not functions of where I was. All right, that's especially convenient. And you can see now that this actually then gets the entire same structure as even the XY model. This phase here, right? This phase, this is single valued. But can everybody read this? All the way in the back, you can read this? Okay. It's single valued, but g dot u is not, isn't. Because g dot u can change by 2 pi as they go around the cycle. That is a topological defect in a crystal. It's exactly the same as the topological defects in the XY model, right? And for each independent reciprocal lattice vector, I can have a defect where as I go around, g dot u changes by an integer multiple of 2 pi. Okay? And there'll be some point where I don't know what's going on. So you can even classify these kinds of defects, which by the way are called dislocations. These are called disclinations. They used to be called disinclinations, but I don't know, somebody thought that was a bad name, probably physical review. And so they removed the term disinclination and turned it to disclination. And these are dislocations. I'll remind you what a dislocation looks like, right? I'm going to do my favorite system, which is a smectic liquid crystal, the case of the smectic. And a smectic is just a one-dimensional crystal, except I should have been careful. This is the dimension of the crystal, not the dimension of space. I can have a one-dimensional crystal living in 3 dimensions. It'd just be a set of planes, stack of cards. That's what a smectic is. That's d equals 1. And what would it look like to you? So I have sheets, like so. I have to tell you, I learned to draw parallel sheets when I was in graduate school. And you might say, why would I do that? Do you know why? Because there were these conferences. I think they still exist. They're in Rutgers, New Jersey. No, well, I guess they're at Rutgers University. They're statistical mechanics conferences. And part of them is this rite of passage of the 2-minute talk. You have to get up and give a 2-minute talk with no visual aids other than the chalkboard. Even in this day and age where you could actually email your PDF ahead of time, no, it still has to be a chalkboard. So you had to practice giving your talk to your advisor at least 10 or 30 times, 10 to 30 times. It didn't take him that long. And you'd have to be able to draw whatever interesting picture you were drawing. And so you had to learn how to draw fast. You couldn't think about it. It had to just come out. Okay, anyhow, this is the ground state of the smectic. And then what you can do is you can imagine a situation where you add an extra layer, like so. So another layer just gets inserted in. So there are many universities that are like this. Many of them are in this country. So who's ever been to Bristol? Raise your hand. You've been to Bristol? So Bristol has an old building and a new building, and they're attached. And one building has an extra floor, right? Because there's a pre-war building and a post-war building attached. And after the war, apparently, we needed to have smaller floors. Everybody shrunk, or whatever it is that had to go between the floors got smaller. And so post-war buildings have more floors, so they're the same amount of height. And they had to glue them together. And so they have one extra floor here. And remember, it's called the mezzanine, right? So you add an extra floor. So people do this all the time. All right, in the U.S. we're filled with it, right? And in fact, most interestingly, in Bristol, these things are connected in the center by a screw dislocation, another kind of delicious defect right up the center. There's a stairwell, but that's an aside. So that's what a dislocation looks like. And let me see how that works. I start here. Oh, I know use a different color. I start here, and I go down a floor. So I'm dropping down to see my colleague on the floor below me, and I come over here. And I go up 2 floors, and I certainly expect that if I walk back down the hallway, I'll be visiting my colleague that's 1 floor above me, right? So, you know, there's me. Okay, I can draw the next floor. I can't now because I already drew this floor, but there's this floor up here, right? I certainly expect to be here because I went up 2 floors, but I come back down the hallway and I think, oh no, I must have been thinking too hard or doing something wrong on this stairwell, right? And so I am dislocated. I find myself in the wrong place. I think I'm here, but I'm here, okay? Really, I think they should be called mislocations, right, for that, but it's okay. That's what they call them. So here you are. You're sitting here. So there it is. There's the crystal. And what's happened as I've gone around, what's happened is that this g dot u has actually added an extra 2 pi. Slowly and surely, as I've moved around, I've actually jumped ahead 2 phases, 2 whole cycles in this phase instead of 1 whole cycle. right? I went from here to here. I went backwards by 2 pi. Like this, I'm staying constant. And now I've actually gone up by 4 pi. And I come back. And I've actually given a shift in myself. And you could ask yourself, where's the defect? Anybody? Raise your hand if you know where the defect is. Yes? Because you don't know what floor you're on here. Right? Everywhere else I can assign a floor, but right here I can't. Actually, everywhere else I can at least locally assign a floor. Right? But then here I can't. Okay. So, oh my gosh. So the reason I wanted to talk about the ground state manifold is I just want to remind you, oh no, this chalk is very expensive. Okay, so I wanted, there's no eraser. Okay, I wanted to remind you of why the ground state manifold is so interesting. And it'll be perfect. This will be done. And we'll have our coffee in 10 minutes. And oh no, I have till 10:30. I can't remember anymore what I'm doing. When did I start? No, I don't have till 11. You missed it. I have till 10:30. We changed it. Peter approved it. You can give Peter. We're going till 10:30. Right. Peter approved it. He sat in the back. He said yes. Okay.
Well, he also moved the T to 10. So maybe they're going to change it again.
No, they understood. It was a miscommunication. I'm going to lecture till 10:30, and then I will give you the final half hour, starting at 10:45 till 11:15. That's certainly what I meant, and they understood it back there. Okay. So let me just then let's see if I can do it without any notes. No, that would be silly. Right? Let me remind you about Goldstone's theorem. And the reason I want to do this is I really want to drive home this idea. This ground state manifold, which is the manifold that I traverse as I go and make a topological defect. You get it? I go around the ground state manifold. I make a non-contractible loop around the ground state manifold, and that is what gives me a defect. And that's why it's topologically stable, because pi 1 isn't 0. Does everyone know what I'm saying? I take a path around my building, that blue path, all right, and as I do that, the phase actually winds by 2 pi. And there's no way to unwind that phase smoothly. So there's no smooth way to remove what I just did. But of course, this ground state manifold and Goldstone's theorem are intimately related by this double arrow. So let me remind you about Goldstone's theorem, which is important. And actually, everybody's been talking about it, because that's what hydrodynamics is about. So Goldstone's theorem says, suppose I have a free energy functional that depends on phi I, and there's a symmetry, right? With a symmetry, I always put it in afterwards, with a global symmetry, right? F of Rij phi j is F of phi I. In other words, if I take the phi i's to be, if I take phi I to Rij phi j, then the free energy is invariant under that. There's lots of free energies that are invariant that way. In fact, almost all of them, right, have interest. All the ones that are interesting have interesting invariances, like rotational invariance, right? So if I have a vector field, n, then of course the free energy, if there are no aligning fields in space or anything like that, if I have a vector field n and I rotate it, the free energy should be invariant under that. And I could certainly write it down in terms of this, and this is just like a rotation matrix. So that's not so interesting. Phi, of course, they're functions, right? Just to remind you. But this is the last time I'll remind you. They're functions, okay? But I have this global operation on R, all right? So I do a global rotation. Oh, I missed the word L. Global symmetry, okay? So what can I tell you if I have such a free energy? Well, let me now expand Rij. How can I expand Rij? What could I possibly mean by expand? In the case of a rotation, Rij can depend on some parameter. So I'm going to expand it. I can only expand it, of course, if it depends continuously on the parameter, right? So, of course, one of the symmetries I can have is one of those pneumatic symmetries I told you, which is you can take n and turn it into minus n. Remember that one? Right? That's boring. That would be a matrix with all minus ones on the diagonal. And that might be all I have. I might just have reflection symmetry. I might just have an Ising variable. Phi might not have an index. Phi could just be the magnetization in the Ising model, and the symmetry is I can take phi to minus phi. And if I so chose, I could write it like this with a matrix. Okay? But I'm not talking about that. I'm talking about now continuous symmetries. Right? So it only gets interesting if I can expand this for small epsilon. So Rij has to be continuous. So the first term is the identity, which I can write identity ij. And then there's going to be some order epsilon piece epsilon times aij plus order epsilon squared. Okay? So now I'm making a further assumption. I had a symmetry. Now it's a continuous symmetry. That's so important, I'm going to write it in red. I'm going to do this thing to remind you, right? So now I'm assuming not only does my free energy have a symmetry, it's a continuous symmetry, which means I can expand it around the identity. Okay. Well, oh, I've lost the eraser. Oh, it's up here. So since there's an since there's an identity, right? Since I have this condition up top, I can expand it too. So this tells me that f of phi I is equal to f of, ready for this, phi I plus epsilon aij, aij phi j plus order epsilon squared. So now I'm being sloppy. I'm saying, well, it's only, I'm saying, I now say these two things are true. Of course, the corrections are going to be order epsilon squared. Somebody's grimacing at me. You don't like that? I am making an assumption about my function. It has to be nice. It has to be analytic in phi, whatever that means. Whatever it means to be an analytic functional, that has to be one. So now I'm going to expand both sides. I think the next step will fix it anyhow, right? So now I expand, and I write f of phi I is f of phi I, right? I mean, let's put it like this. And now he's happy. F of phi. Now I'm going to expand, and the first term I get is the order epsilon piece. And what happens when you expand a functional? All right. Now I have an integral over all of space. I vary the functional with respect to phi I of x and phi j of x plus order epsilon squared. Okay? Everyone get it? Yes? Question?
Don't quite get this.
Which part?
First term equals first term plus stuff.
This is this. Now I'm expanding this side.
Ah.
So, yeah. I should. I'm expanding this, all right? So I'm just going to set these two equal, and of course now I'll be able to cross out the first term, which is nice. And so, I know this is a big sloppy mess. Everyone read what this is this. Okay? So it follows that f of phi I equals f of phi I plus epsilon times this integral d dx df d phi I of x aij phi j of x plus order epsilon squared. Does everybody understand why I have this integral? Right? It's a functional, right? So this is just a gradient, right? And the index of the vector field is just the point in space. I know it's a really sloppy and terrible way of saying it, but too bad, right? It's as if I have a big vector field, phi, labeled by x as its index, and so I have to sum over that index in whatever dimension I'm in. So it follows that epsilon times this integral, or it follows that the integral d dx of df d phi I of x aij phi j of x is 0. Because it has to be true order by order. If a Taylor series in epsilon is 0, then each term has to be 0, right? So it follows that that has to be 0. And by the way, I'll write this down for you once and only once. Okay? I can't help myself, all right? They're the same symbol. Okay? All right, I'll try not to do that. This is the first error, right? It's the first time yeah. Okay. So this is kind of a cool equation. Notice that if I expand around the minimum of the free energy, if I say, oh, well, let me expand, what phi should I choose? After all, this is a whole functional of phi. I have to give you the function phi, put it in, and that has to be 0 for any function phi, right? At the ground state, it's automatically 0. In the ground state, df d phi vanishes, right? Because that's the Lagrange equation, or that's the variational principle. You look at the minimum of the free energy, right? For phi I equal phi I star, that's the ground state, or any ground state, df d phi is 0 anyhow. So that's not that interesting. But let me keep going, because what I wrote down did not depend on the ground state. I didn't say to you that the free energy had this symmetry only if phi was the ground state. I said the free energy had this symmetry, period. It was just an algebraic fact about the free energy. It had nothing whatsoever to do about the ground state. Okay? So let me continue. So this is still a function of phi. Just happens to be 0, but it's still a function of phi. So let me vary it again. I figured it all out. In my country, where I come from, we call this an eraser. No, in my country, we have only one tray for the chalk and the erasers, even when we have chalkboards that move up and down. And that's what's getting me confused. Probably Daryl, too, right? Does everyone understand what I'm saying? You could have one tray and the chalkboards move up and down. And you know what the problem with that is? Anybody? Stuff drops into the hole behind it. You never get it out. All right. Until you rebuild the building. So let me vary that again. Let me vary again. So let me take d by d phi k, d by d phi k, phi sub k at y of that whole equation. So what's d by d phi sub k at y of 0? How does 0 change when I vary the function? It's a trick question. Answer? 0. It continues to be 0. So one side's still 0. But now I can vary the other side. Now I have the integral d dx, d squared f, d phi k of y, d phi I of x, aij phi j of x. And of course, you're thinking, is he going to just keep doing this? Is he going to just keep function driven? I could, and I could spend I could spend a whole day doing it, and I'd invent all sorts of notation, and it'd be very exciting, but I'm not going to do that. I'm going to stop here. Now I'm going to do something else. Oh, I'm sorry. How sloppy. I forgot the other term. The other term is, so I still have d phi I of x. And now I have, aij. And what do I have? I have this variation, whatever that variation is. That variation is delta d x minus y delta jk. Agreed? In other words, when I vary this, I could vary this guy, but I can also vary this guy. And if I vary the function phi j of x with respect to phi k at y, that is a delta function in space when x is equal to y, and the index j has to be equal to the index k. It's a delta function in all things that are good. Okay. And like I said, I could keep going. It would get quite complicated. I'd have to vary this. I'd get all sorts of terms, right? I would end up for you rederiving. Are you allowed to call it Leibniz's formula here? You know what I'm talking about? Are you allowed to call that here? You are, even in this building. Okay. All right. So what? So let me stare at this equation. Now, evaluate at phi I equals phi I star. I'll remind you, df d phi I at phi I star is 0. That's the ground state, or it's one of the many ground states. So when I evaluate it at phi equals phi I star, this term vanishes. See it? It's 0 anyhow, because this term's 0. And I now deduce that when I evaluate this at phi equals phi star, it follows that 0 is the integral d dx Okay? So that's it. So important, I'll put a box around it. Okay? So that has to be 0. That has to be 0 for any ground state. When I evaluate this for any value of phi star that's a ground state, this has to be 0. So here's the neat thing about this equation. All right? So the neat thing about this equation is that now assume, you ready for this? One more assumption. I'm being clear what the assumptions are. I know you think I'm putting lots of assumptions here, so it must be not a very general thing, but my assumptions are pretty general, all right? But I want to be careful. Assume translation invariance. By the way, that's why I want to have an Eulerian description of my crystal, because then that is translation invariant automatically, right? So that's part of the reason that that's a good reason to use Eulerian description. Assume translation invariance. If I have translation invariance, then the expectation value, or the value of phi I star at x, has to be equal to phi I star at x plus delta. Do you agree? If it's translationally invariant, then it must be that the ground state solution is the same here and here. That's what I mean by translation invariance. And if that's true, then phi I star is a constant. Doesn't depend on x. So this is assuming that the ground state is actually translationally invariant. And so Now I get something good. Because if phi I star is a constant, I can pull this thing outside. And now I have the following interesting equation, which it doesn't bother you guys that sometimes the zero's on the left and sometimes the zero's on the right. Good. It shouldn't bother me either. So I have integral d dx d squared f d phi I of x d phi k of y. Now I'm going to put parentheses around this, just for fun, times a I j phi j star is 0. Hey, look at this. This is a matrix, right? You see, this is a matrix with the indices I and k. And this is a vector. As a matrix times a vector is 0. When a matrix times a vector is 0, it is only possible, it's a symmetric matrix, by the way, it is only possible when either the vector is 0 or there's a 0 eigenvalue. I have one or the other, but not both. I could have both, I guess. That would be terrible, right? But I certainly have to have one or the other. And so the pretty thing here is, first of all, because of translation invariance, this can only depend on the difference between x and y. Let me call it gamma gamma ik of x minus y. Right, so that's some matrix, like so. Yeah, I'll write it like that. And then this equation here becomes the integral d dx of gamma ik of x acting on aij phi j star is equal to 0. And again, you're saying I could go on forever making these changes of variables, but I'll remind you that this integral has a meaning. Anyone? Here, I'll make the integral have a meaning by changing it for you. Okay, ready? Okay, I'm going to add to this the integrand e to the I k dot 0. No, sorry, e to the I 0 dot x. Okay? So 0 is just the 0 vector. And x is, of course, the same x that I have here. All right? Now can you tell me what this integral is? Some people are smiling. I have children. I know up until 8 weeks old, that just means they have gas. They're not actually smiling at you. But I don't think that's what it is. So would anybody care to tell me what I mean, why I wrote it like that? Come on. I mean, you can guess. It's not it is being recorded. But it's okay. Don't turn the camera on the audience. Keep it on me. We won't know who said what. Come on. Trying to engage you. Do I have to call in the same people? I'll call you. Because you remembered your breakfast.
Oh, me? Oh,
Yeah.
I really have no idea.
It's the Fourier transform of this function at k equals 0. Ah, look at that. Isn't that cool? See, when you integrate a function over its everything, that's the k equals 0 component of its Fourier transform. So this actually has a meaning in Fourier space. This function, this matrix, which I could call M for matrix, MIK, MIK is precisely equal to this in Fourier space at k equals 0. Right? So this is MIK, and I have MIK times this vector VI is 0. So either MIK has a 0 eigenvalue or V is 0. The only way that V can be 0 is if phi star is not, sorry, the only way v cannot be 0 is if phi star isn't 0. Agreed? I mean, of course, somebody's going to say to me, well, you could have the case that aij is 0, in which case the symmetry doesn't act on anything, so I'm not interested. Okay? So I wouldn't be interested. So I need to have aij has to be non-zero or we're done because there's no symmetry to begin with. And so now I'll say if phi j star is non-zero, then this vector is non-zero, and it follows that this has a 0 eigenvalue. Okay? If phi j star is 0, then I don't have to do anything. All right? So what is this? Everyone see the picture in their head? I'm going to draw the picture here. Right? I have some potential. This is the usual story. I have some potential like so. Okay, it looks like the bottom of a wine bottle, right? Yeah, it looks like the bottom of a wine bottle, like so, or a soda bottle. And what it's telling me is I could have a solution here, right? This whole potential has a symmetry, a rotational symmetry around this axis. I can have a solution here which has the symmetry of the ground state automatically because phi is 0, or phi could choose to sit somewhere down here, and phi star is not 0, and then it means I have a 0 eigenvalue. And you know what it is? It's the one where I go around the bottom of this well, right? Yes? Does anyone have a good name for the bottom of this well? I've already told you a name for it today. See, that's the ground state manifold. Okay? The ground state manifold is the place where you can go around the bottom. It's all the different ground states that are related by the global symmetry that we talked about in the first place. So a topological defect is something that's going around the bottom of the wine bottle, right? Or a multi-dimensional wine bottle with a complicated geometry if you're talking about more exotic defects. So the ground state manifold, the Goldstone mode, which is the mode that moves around this way, is precisely the thing that's moving when you're moving around the ground state manifold. That is the coordinate. The coordinate of the ground state manifold is given to you by the Goldstone modes. Those are the directions in the ground state manifold. And let me finish by proving Goldstone's theorem now. Let me remind you that if, right, again, here's another note, right? I had phi I goes to rij phi j. Well, of course, if phi I is 0, then there's no content here. If the phi's are all 0, right, then this is an uninteresting result. It's only interesting when the phi isn't 0. The symmetry, right? Only interesting when phi is not 0. So, oh, here, I had this as the result I wanted, right? So why is that good for me? That's good for me. Good for you. It's good for us all because I can now imagine looking at my free energy again. Let me go back to my free energy. So here's F of phi, Gesundheit. And as you all know, it's completely inappropriate to expand the free energy around an arbitrary place. It makes sense to expand the free energy around the ground state. And then you look at fluctuations around the ground state. You don't want to be in a situation where you're at the top of the hill and you expand around the top of the hill only to find out that you have these horrible negative directions that you want to slide down. You want to find a minimum and expand around there. And of course, that's what Taylor series is all about. And so I'm going to expand f of phi around phi minus phi star, which I'll call delta. I don't want to call it delta phi. That's terrible. I'll call it psi. All right? So psi I is phi I minus phi I star. So now I'm going to expand my free energy around the ground state, which is what you're supposed to do. So I might as well have it be a free energy functional of psi, right? It's the same as the free energy functional of phi I, like so. What do I get? Well, the first term I get is f of phi I star. That's just some number. That's the background free energy. It's something. It could be very interesting. All right? It has all that entropy living in it, all that ground state entropy. I don't know. It's interesting all by itself. There it is. And now there's the next term. What's the next term? It's a trick question. You could say, yes, the next term's 0 because it's the first derivative, and I'll say, yeah, so that's not there. The next term is the second derivative. But let's say whatever answer you gave, I could have given you a hard time. But yes, the next term is the integral d dx, like so, psi I of x df d psi I evaluated at phi I star, which is the same thing as evaluating at psi I equals 0, of course. Okay? So I'm being fast and loose about this. Too bad. All right? There's the next term. This, of course, is 0 because it's the ground state. And the next term, most excitingly, is the integral d dx, d dy, psi I of x, psi k of y, d squared f, d psi I of x, d psi k of y. And it's evaluated at psi equals 0. Plus higher order terms. Okay? So the free energy that I'm interested in, it has a constant piece, whatever it is. It's just a number. It has no term here, linear in psi, and the first correction is quadratic in psi. And I'm expanding around a minimum now, I hope. I hope that that's the minimum. All right? I'm expanding around an extremum. So here's my quadratic term. Hey, has anyone ever seen this before? And you can tell me. Anybody? Yes or no? Yes? Yes, point. It's all over the place, right? In particular, I define it right here. It's gamma, right? So why is that interesting? Because if my whole theory is translationally invariant, then I deduce that f of psi I is f at psi equals 0 plus the integral. Now I'm going to turn this into an integral in Fourier space. You ready? I love Fourier space, okay? I have the integral d dx, the integral d dy. I have psi I of k1, psi k, I'll use q, right? q1, q2, gamma ij, gamma ik of q3, like so. I have to have lots of integrals here. I should have planned ahead. You don't have to do this. I'm just doing it. All right. Plus, so I have the integral ddq1 on 2 pi to the d, ddq2 on 2 pi to the d, ddq3, 2 pi to the d, ddx, ddy, psi I of q1, psi k of q2, gamma ik of q3. You ready? E to the I q1 dot x, e to the I q2 dot y, e to the I q3 dot y minus x. And I only chose y minus x instead of x minus y to make the formula look pretty, but that's dumb. Okay? In other words, this is a function of x minus y, this is a function of x, this is a function of y. And now I'm free to do the x and y integrations. The x integration gives me a delta function times 2 pi to the d, which sets q1 equal to q3, q1 equal to q3. And then the y integration sets q1 equal to minus q2. So there's only one q integration left. The two x and y integrations kill 2 of the q integrations. All the 2 pi's go away. And we're left with, timing is perfect here. We're left with f of psi is f of psi equals 0 plus the integral d dq on 2 pi to the d psi I of q psi k of minus q gamma ik of q. How nice is that? Because I know something about gamma ik of q. What do I know? I know that it vanishes at q equals 0. Right? I just showed you it vanishes at q equals 0. Right? But gamma ik at q equals 0 is 0 if phi star is not 0. So when I have a broken symmetry, and broken symmetry means that the solution does not have the symmetry of the ground state, then when I expand, I find that I get this special expansion, and I have some special thing. This function here, this kernel, vanishes at q equals 0. And if I have any vectors around or any special directions, then I know that gamma ik of q, well, is there a constant piece? No, I just showed you there's no constant piece in q, right? There's no linear piece because I would have to have a vector to contract against the vector q. So there's no linear piece. So the first term I get is some number times q squared plus order q to the 4th. And that's what Goldstone's theorem is about. It's telling me that there are these coordinates, but when I move in those coordinates, the energy is extremely small. How small? You can make it as small as you like if you let q be as small as you like. So if you make a very, very, very long wavelength deformation, you can make the energy as small as you like. All right? And that's what Goldstone's theorem is telling you. And that's why these are the natural coordinates. It's easy to make a defect. If I move around slowly as I like, I can make that defect have very low energy. Those are the coordinates I'm moving in. Those are the coordinates of the ground state manifold, psi. Right? And the energy is quite low. I don't have to like push something over a hill to go from this ground state to that ground state. I get to move as slowly as I want. And so let me end. So it tells me that my free energy in psi has some constant part, f of psi equals 0, plus something that looks like this. Back in real space, it looks like the integral d dx. It looks like gradients of psi I, gradient of psi k, times some matrix, gamma ik. Okay? And I just get gradients. I get one gradient each. That's q squared. So I get this gradient free energy. Right? And I had one last thing to say about this, which is suppose that I were trying to do hydrodynamics. What do I mean by hydrodynamics? Suppose now, so everything I've done here is about statics. Suppose I did some dynamics, and suppose my dynamics were just relaxational dynamics. So I could write something like this. d psi dt is minus df d psi. I know I could put a coefficient here, but everyone would want me to put the symbol gamma. So that's bad. So I'll put gamma here. I'll put the viscosity here. Okay? There's some viscosity, right? This is just some kind of relaxational dynamics. What can I tell you about df d psi? Or rather, what can you tell me? I can tell you all sorts of things. Can anybody tell me what df c psi looks like? Come on, it's not a trick question. You have everything up there. What's the first term? There's no constant piece, right? So the first term, it's linear in psi, because the free energy has its first term quadratic in psi, right? So the first term is going to be varying this guy. And when I vary this guy, I'm going to get something, which is going to be some number, I don't know what it is, something, some matrix with some indices I and k. If I like, I can put an I here, right? Ik, like so. And what I'm going to have here is del squared of psi k. And so, if I stand back and look at this equation and ignore all the coefficients, which are all constants, I deduce that d psi dt is the divergence of something, which depends on grad psi. Right? I guess I can write like this, d psi dt aik. And so I have a conservation law. Right? This is the flux. Or the current. Yeah, the current. Or the flux. And this is another way, a roundabout way, of getting Noether's theorem. Right? The conservation law follows too. Usually you start with, if you have a conservation law, if you have symmetry, it gives you a conservation law. And then there's this extra bit, if it's a global symmetry, a continuous symmetry, you get Goldstone's theorem. But you can actually start with Goldstone's theorem in the first place. Right? Goldstone's theorem automatically implies the conservation law, just from the structure of the free energy. That is to say, another way, a sloppy way of saying it is if I expand the free energy, it can only depend on gradients of psi. And since it only depends on gradients of psi, whatever dynamics I write down will always have a divergence in front of it. So there you go. That's Noether's theorem, I guess. Anyone know where she's from? No, I'm sorry. Do you know where she's buried? Nobody? Do you know where she's from? Does anybody know where she's from? Does anybody know who her advisor was? Has anyone ever heard of Emmy Noether? Raise your hand. Okay, so who was her advisor? What? I have no idea, but I thought somebody would know. What? Wasn't she a Göttingen?
Who was Hilbert?
Sorry?
Wasn't it Hilbert?
I think it was Hilbert. Okay, but she's buried just outside Philadelphia. She's a professor at Bryn Mawr University, right? And she's there. And I'm trying to get them. I think they should have an entire conference. They should have an annual conference on hydrodynamics, right? Sponsored by the university or the college. It's a very rich college, right? And then we could all go, right? We wouldn't do it in the summer where it's hot. We would do it in the spring where it's nice and comfortable, right? It would have to move because spring only lasts 3 days in Philadelphia, but right, it goes from winter to summer very quickly. But anyhow, there you go. You have Noether's theorem. So you see that broken symmetries give you Goldstone modes. Goldstone modes naturally give you conservation laws, local conservation laws. But most importantly, what I hope I've gotten across to you is that these are all the same thing. These are the coordinates on which you move in the ground state manifold. These are the coordinates that carry the topological defects. If there weren't Goldstone modes, you couldn't have topological defects. At least the kind I was talking about. Okay, so it's like next time. Next time will be in 15 minutes, I suppose. I know I'm jumping you, right? And I think I will talk more. I'm going to talk a little bit about geometry, and I'm going to show you some videos. Okay? So, thank you. I just want to, I feel like I could go on forever and tell you more about topological defects, and I could. Oh, haha. Thank you very much. See, I remember. So, I could keep talking about this stuff. There's lots to say. I would say there's so much to say that not all has been said yet either, although you might think that it has. But let me just tell you about some applications of these ideas, which might pique your curiosity some, and someday you too will decide to spend your time thinking about these things. So let me tell you about some work. So Eugene Terentev, a local hero, who back in 1995 said, well, suppose I had a three-dimensional nematic. Okay? And so those thin lines, those are the directions of the pneumatic. Far away from whatever's going on, the pneumatic is neatly aligned so all the molecules are pointing up and down. Okay? He says, suppose I put a sphere, it could be a colloid, it's just a single sphere, which has these boundary conditions. The boundary conditions are such that the molecules want to be perpendicular to the surface of the sphere. It's called homeotropic anchoring. And it's only after, working in this field for 20 years that when you say homeotropic to me, I immediately know what that means. I always have to look it up. Okay? But there it is, homeotropic. It means they're all pointing perpendicular to the thing. And he said, well, if they're all pointing perpendicular to the thing, simple geometry just tells you that's impossible. Because if I just think of those as lines of, say, electric field, I know it's impossible to have a point charge in the middle with field lines going out that eventually goes to a constant electric field. Right? If it's constant electric field, if I did a Gauss integral, I would get some charge. I would get no charge inside, right? So it must be that there's something going on. He said, oh, but look, see pneumatics. Pneumatics enjoy something that almost no other system does, which is they also can have line defects. Pneumatics can have point defects, but they also can have line defects. And we discussed this last time where I said pneumatics can have charge 1/2 defects. And here's a charge 1/2 defect. You see, as I go around this black line, right? Think about it in the plane first. The direction rotates by minus pi. If I go around clockwise, counterclockwise, then the molecules will rotate around clockwise by pi. And he said, so now you take that two-dimensional picture and you rotate it around this axis, and you discover that you have this ring, the ring of Saturn, the Saturn ring, which completely screens out the charge. If you think about it now, there's a singularity here, there's a defect here, there's an imaginary defect at the center of the colloid, but then far away everything's just hunky-dory. And there you go, there's a solution that only pneumatics can have, because pneumatics get to have lines and points as their defects. A couple of years later, turned out it was hard to make these. Nobody saw, apparently nobody saw these in experiment. But a couple years later, Philippe Poulin and collaborators at Penn, they said, well, if I put a colloid in with that same boundary condition, I don't have to have a ring. I can have just a point screen it. Of course, this would be true even in a vector system. And then, of course, you can see this is like a dipole in an electric field, right? So, or if you like, it's a stagnation point in some kind of fluid that is squirting out of the sphere here. And so you get this point here, which this is not a colloid or a water droplet like this is. This is just a point that's required by the topology to be there, so that far away the director fields are all nice and parallel. And you get these dipoles, right, in the pneumatic. So these are topological dipoles. There's a point charge here and another point charge there. And you can imagine doing that integral that I told you about and calculating the degree of the map, and the degree of this map would be +1 and the degree of that map would be -1. If I looked around this black point, I would discover that it was going around the pneumatic direction backwards compared to this one. Right? It's wrapping around that sphere. I can wrap around the sphere in the positive sense or in the negative sense, and one of them will be in the positive sense and won't be in the negative sense, but more importantly, in the experimental sense, there it is, okay? And they actually get these chains of dipoles, and I hope you can see, here's one in the center of a sphere, here is a chain of them, here is the water droplet, and then in between the water droplets are these tiny little points. Those are the little screening charges. Okay, so this is state of the art back in 1997. And now let's move to this millennium, okay? And I want to point something out about this picture. First of all, it's in color, okay? It's a theory picture in color, as opposed to experimental pictures. Of course, they've always had color. Even back in the day when they had black and white film only, everything apparently was still in color, right, is my understanding. Tom Lubensky tells me that, back then, that when he saw things, they were in color, even though the photographs were black and white. But here, this is a color photo figure made by an experimenter, a theorist. And the other thing about being in color is I don't have the director field anymore, right? All I have is here are the colloids, and these lines here, those are the topological defects that Eugene had suggested back here. And let me tell you why this is important, right? The defect, the lines of the field are an unnecessary encumbrance to everything you do. If you want to manipulate the defects, you need to have a set of tools that allows you to manipulate and think about the defects without having to always draw the field. Because it's a complicated three-dimensional field. Very difficult. So here's a situation where you take these things, and now we're trying to imagine a world where the defect lines themselves are the interesting objects, where we manipulate them. So to the point that this group in Ljubljana did this absolutely stunning work where they took whole arrays of colloidal spheres, and then using laser tweezers, they were able to reconnect the way that the spheres were wired together by these disclination lines, and were able to construct all possible knots up to some number of crossings, X crossings. It was like 5, but that was only limited by their patience and the size of their colloidal array, right? And so they're actually able to make knots and make all these different knots. So they're actually able to tie the defect lines together. And let me explain to you, or try to have you visualize how cool that is, okay? Because you know you can tie knots and strings. But now the whole field, the whole pneumatic field around there has to respond to it. In the fluid, if I were thinking of this as a vortex in a fluid, the entire fluid flow needs to respond as I move those vortices around. It's not just that I have these lines. These lines are telling me about some global kind of winding of the pneumatic field. So there's something really complicated. The whole field is knotted, not just the lines. Okay, so here are the people I worked with. There's lots of them, okay? I think I would say, of the things I'm going to tell you, Brian Chen's the hero, all right? They're all heroes. That's rude. But I'm going to tell you a lot about work in Brian's thesis, which I think really goes a long way in making this, this into a reality of not having to see the director field. So I already showed you this picture. I'll zoom through it, right? Here's that Schlieren texture. Look, now you know everything. You see the defects, right? The defects, I showed you this already. Blah, blah, blah. Right? Okay? I showed you this. But now maybe it has more meaning. This is the manifold of ground states. This coordinates on here. What are the coordinates on the manifold of ground states? Anybody? The Goldstone modes, exactly. See, now we know what they are. They make the local coordinates. So, like I said, there's this thing about defects in pneumatics. Defects in pneumatics enjoy, they get to have both line defects. That's places where I wind around and the molecule changes its direction by pi. And I also get to have point defects. Those are situations where as I go around the sphere, it points in all the directions on the image sphere. And so when I go from 2 dimensions to 3 dimensions, I can either extend those points into lines or keep the points as points. And now I have maps about the first fundamental group, winding on the circle, and also winding on the sphere. I get to do both things. So let's go back to Eugene's picture. So you might have naively thought something which isn't true. I would have thought it too. In fact, I thought it until very recently. Here's this colloid, here's this Saturn ring. You might say, oh, okay, so somehow the colloid has charge 1, and it must mean that the Saturn ring has charge -1, and somehow they cancel. That would be a very Gauss's law electromagnetic way of viewing things. But I warned you that that's not true. I warned you that on Monday. It's not true. Because it turns out here are 2 different simulations. All right? So what you do is imagine you bring 2 of these together, two Saturns. You bring them together. You have a colloid and a colloid. They have their Saturn rings. You start bringing them together. What happens? Well, sometimes, I mean, there's energy that forces the lines not to, be exactly parallel. They distort. So on the left, you see a picture where I have 2 colloids, 2 Saturn rings. And at far away, I have uniform director. But on the right, I also have a uniform director at infinity. But look, I only have 1 Saturn ring. So saying to me, oh, the Saturn ring must have charge -1 to screen the charge +1 is somehow a little too simple, because somehow this Saturn ring, this single ring, actually screens the 2 charges also. You have a question, or are you imitating a unicorn?
Is there like a Fuller-White theorem that applies to the rise of a...
Well, yes. And so Simon Chopard, that was what his thesis was about. But that's specialized. Okay? So as Peter, or as Professor Olmsted correctly points out, obviously the information is somehow encoded in the shape. But I'd say no, it's really encoded in the whole field, right? And the shape reflects that, right? So maybe we can try to understand this. One thing that I want to add, is that a funny thing about pneumatics, or a wonderful thing about pneumatics, I said you can have this winding, and I showed you on Monday you can have a winding of 7 pi or 8 pi or 9 pi. Pneumatics in 3 dimensions are funny. So here I have a situation on the left where I have a -1/2 disclination. You might think if I go around here, I rotate by pi in the opposite direction that I traverse the circuit. Here, on the other hand, I have a plus pi defect, right? If I go around counterclockwise, then the rods also rotate around counterclockwise. But pneumatics live in 3 dimensions. Watch this. You watching? Look at the thing on the left. What I'm going to do is I'm going to rotate every single molecule along this axis. The axis here. I'm going to rotate them by pi. I'm allowed to do it. That's a smooth deformation. That's a homotopy. I'm allowed to do that. It doesn't change anything. I'm going to smoothly go from the thing on the left to the thing on the right. What that's telling me is that pneumatic defects only have yes or no. The line defects are either there is a defect or there isn't a defect. It doesn't have any winding. And that is a subtlety that comes about because it lives on a sphere. And I encourage you to read any number of articles about that. There was a Review of Modern Physics article co-authored by me and some geniuses, and you could go look at that. I don't know, it's like a couple years ago. You could look at that if you want to read about it. The point is, these are the same. See, they're the same configuration. They have exactly the same topology. So either there is a defect or there isn't a defect. And that's all I can tell you. So I can have this defect line. There it is. There's a defect line. There's no other information on that defect line about how much wrapping there is. I can't say I go around 7 pi or 8 pi or 37 pi. I either have one or I don't. And there's many different geometries that I could give you that would have a defect there, but they're all equivalent under homotopy. So the nice thing about the disclination loop, like I tried to say at the beginning, does it have a charge? Does it have a charge that can screen the charge of a point defect? Well, how do I know? Well, one thing I do is I put in a torus, but really I'm going to put the whole thing in a sphere. In other words, I imagine this thing as an object, and now I surround it with a sphere, and I make a measurement. Here are those maps from the sphere to the sphere. You see this sphere? See the red sphere? Everywhere on the red sphere, there's a direction of the pneumatic field. So that's the S2 on this side, and then there's an S2 over here, and there's a map from that S2 to that S2, and it has a degree, and I can measure the degree of the map induced by this defect in the middle. Okay? So what can you do with that? So Ivan Smolyak and Bohdan Senyak, they did some beautiful work. It took them many years of hard work to actually make colloids that were the shape of a torus. Instead of, sphere colloids, they made torus colloids. Okay, isn't that cool? I guess mathematicians call them handle bodies because they're solid. It's not just the surface. There's the whole inside. Okay, the difference between a torus and a donut is a torus has 0 calories, but a donut is filled with calories. Okay, so here you have this colloid, and they arrange things so that they have exactly the same homeotropic boundary conditions. The molecules always want to be perpendicular to the colloid. Okay, and you say, isn't this great? So what do you get? Here are pictures. These are even better than cross-polarizers. These are quarter wave plates, but the same information is there. This is telling you how the molecules are rotating around. Sometimes you get a point defect right in the middle, and things rotate around. Sometimes everything's nice and straight in the middle, and you get a line defect here. So you get 2 line defects. There's a line defect on the outside and the line defect on the inside. Head scratching. How would I imagine, what's the charge of the colloid? Okay, well, the charge of the colloid is given by this integral. I already showed it to you. That is the determinant. N is the director field. If I go out to that sphere, that red sphere I showed you before, I do this integral on that red sphere. That gives me all the information I need, right? That tells me the degree of the map. I can imagine, though, taking this thing, and if there are no defects, I can imagine the following situation. Imagine that I have a sphere out here, and there is no net charge, because I have boundary conditions where everything's aligned. So whatever's on the inside has to have zero net charge, whatever that means. And some of the charge is coming from the surface of the torus. Just like the colloid before gave you charge, the torus gives you charge. So here's the director field. It's homeotropic. I know this looks like one of those icky movies, the images from one of those icky movies where people have nails sticking out of their face, right? But it's the best I could do. So, what's the best they could do? I got it from them. Okay, so here it's going around like this. Here is the torus. And what I could do now is I could measure the charge of the torus. The charge of the torus, is given by something cool. Instead of using little n, the director field, notice that little n, the director field, is the same as big N, the normal to the surface. That's what homeotropic means. So instead of integrating the director field, I can integrate the normal to the surface. And when I integrate the normal to the surface, this is precisely the integrated Gaussian curvature of the surface. That's the Gauss-Bonnet theorem. And the Gauss-Bonnet theorem tells me that this is equal to 4 pi times 1 minus the genus of the surface. So what's the genus of a torus? Anybody? Does anyone know what genus is? Genus is number of handles. Sphere has genus 0. A torus has what? Say it louder. Louder. Genus. How many handles does a torus have? One. One. Excellent. So there's no charge. Right? G is 1. No charge. So what am I showing you? Okay? Notice here, this formula Q equals 1 minus G has QG duality. Right? If I wrote Q like this and G like that, then I can switch them. All right? Anyhow. So that's good. What Yvonne did is Yvonne studied multi-handled handle bodies, many handles, and now these things have a charge. So you're saying to me, why are there defects here at all? This torus has no charge. It's true, no charge. But it turns out, for energetic reasons only, it actually prefers to add a pair of defects. See, defects sometimes have to be there, but sometimes they want to be there. Okay, and they want to be there because that lowers the energy. Sometimes the singularities are put in. When I vary over all possible energies and all possible configurations of the system, I have to include the possibility that the system will choose to have a defect. Right? That sometimes happens anyhow. And so it chooses to have a pair of defects anyhow. And what you discover is, as you look at these higher genus handle bodies, there's always an extra pair of defects. So there's always 2 more than you would have thought, but they are compensating. There are 2 more if you just count how many, but one of them is positive and one of them is negative. And so it doesn't add to the total charge, but it does lower the total energy. So that's kind of an amusing thing. There's defects because they want to be there, and defects because they have to be there. So we wanted to pursue that, and we did. So this is work at Penn, and we said, let's make a colloid, a handle body colloid, where instead of having homeotropic boundary conditions everywhere, it was homeotropic on 3 sides, the tops and the side and the inside, but the bottom was flat. The molecules like to lay flat on the bottom, and so if I drew a picture of the cross-section, the cross-section's a rectangle. The molecules stick out on the top and the sides and here, but they lay like this here. So as I go around, I rotate by pi. So this colloid has a defect living in it. Just like the spherical colloid had a virtual point defect on the inside, this colloid has a virtual line defect living inside it. I've frozen it in, okay? And here is the compensating defect. This is the same compensating defect as they had here. Here was the sphere with the charge. Here was the compensating charge to give you the right far field. Here is the toroidal analog of the whole thing. All right, here we have a torus that has a charge, and it has this outside charge that is required just by topology. That defect has to be there. Okay? Even better, right, is you see that the thing's tilted. It's tilted, of course, because the top wants to be aligned with the far field, and the bottom wants to be perpendicular to the far field, so it compromises and tilts. And then we can do something cool. We can take a single spherical colloid and put it in the middle, and the whole thing lines up. Ring around the colloid, okay? All right, and here it is. And now we've taken the defect in the sphere, trapped in the sphere, and we've taken the defect trapped in the handle body, and we put them together. All right, and you get now a charge-neutral object made all of colloids, and then it's easy to image. So in the last 5 minutes, let me just tell you about this work of Brian Chen's, which is really, I think, is the way we should view things. So here's some 3D texture, quite complicated, okay? And the problem with the 3D texture is I don't know what it's looking like. You can give me sections of it, and I may or may not be able to guess what it is. All right? If I take these things, right, the colloids like that, you have to do a lot of work to figure out the charge of all the defects. So maybe there's a better way. Maybe I don't have to draw the lines in. Is there a way of avoiding the lines? The answer is yes. There is a way of avoiding the lines. I already showed you a way of avoiding the lines. Do you notice here? Do you remember this? The Schlieren texture? The two-dimensional Schlieren texture. I said, you know, you can focus all you like on the whole texture. And I could draw the texture in if you like. But all that mattered for topology were the black lines. There's a one-dimensional subset of this picture that carries all the information about the topology. That one-dimensional subset is not chosen by me. It's not chosen by me taking some section. It's chosen by the system. It tells me which one-dimensional lines to study. Okay? So I could say, here's the nematic in 2 dimensions. Right? Here are the black lines. Now, I'm going to take half the black lines, the ones, say, where the molecules are pointing along the polarizer. I'm going to draw them in with red curves. The blue points are the defects. And now, lo and behold, I can remove the actual director field. What did I just do? This is called the Pontryagin and Thom construction. Basically, what it's telling me in 2 dimensions, roughly speaking, is that if you give me a meromorphic function, a function with a bunch of branch points, I don't know what kind of function that is, a function with a bunch of branch points, I can tell you the whole function up to any entire function. Right? That you give me the information. What information do you need to give me if I tell you have a function with branch points? And I only care about the function up to an analytic function. Right? I say, oh, all you need to tell me are the branch points and how I connect them together through branch cuts. Right? And there are certain moves. Of course, you know the branch cuts aren't unique. There are certain moves called Bordisms that tell me, oh, well, this one and this one give me the same function. But that's okay, right? You can give me all the information. It turns out it's 1-to-1. If I want to know the texture up to homotopy, it's enough to just tell me about these one-dimensional lines. So Brian wanted to extend this to 3 dimensions and 3-dimensional nematics. And so I don't want to go through this. I want to say this. When you go from a point defect here, these curves, these branch points, or these branch cuts ended on branch points. In 3 dimensions, what happens is that line defects, there's a surface, and that surface is like the branch surface. It's a surface, and it ends on the line defect. But I can define the surface another way. That's the surface where all the molecules are perpendicular to the z-axis. So what I'm going to do is I'm going to find the surface in my sample where everything is perpendicular to any particular direction. I'll call it z. That's that surface. Okay? No, every other point has a z component. What happens if I have a hedgehog, a place where all the molecules point out? Right? So imagine a dumb situation where all the molecules just point out radially. So where is the surface? I'll ask you, where is the surface where there's no z component to the molecules? Right. The plane, the equatorial plane. But in the equatorial plane, there's more information because the molecules rotate around by 2 pi, right? So I can color the surface. I can actually put a phase on the surface. And then the point defects are places where I have winding of phase on the surface. So line defects are where surfaces end, and point defects are where there's this color winding on the surface that has its own defect. And so you can do a bunch of things. I need to skip this. Let me get to, is there a way of doing this? I do this so you can't see what I'm doing. And then I come back down to here, like so. And so why is this good? You can take the data that they gave us, and you can study that surface. So you see, I don't have to draw the whole texture here. I don't have to say, here's the whole texture. That texture somehow encodes all the information. This surface that we've drawn in here actually has all the information as well. It's a two-dimensional surface. It's the place where the director is perpendicular to some direction. I don't know which one. It keeps changing because I'm rotating. And then I put this color in because the molecules, they're in the plane, right? And so they have a direction. And I put the color in. And the color winding captures all the information. And the color winding here and the color winding here exactly screen the color winding that you see, the color winding that you get around the sphere. Peter, do you see it? Yeah, so there you see, you can tell it's a point defect because as you go around the sphere, it's wrapping around by 2 pi. And you can do that too. And somehow the wrapping around by 2 pi here and the wrapping around by 2 pi here, somehow they compensate different ways depending on this teeny little twist, which is right here. There's one difference. There's only one place where it's different. Okay? There, and there. And that's it. And there's just some different way that you've glued the surface together. You've glued these color wheels together. And that allows you to compensate the charge at long distances. So this method, the Pontryagin-Tome method, I'm tempted to call it the Chen Pontryagin-Tome method, because then it's CPT also, the CPT method, right, is actually quite powerful and allows you now to understand these textures in a way where the data itself is telling you what to focus on. Sorry, the data is telling you on what to focus. Okay, so I'll end with this. This used to be at a donut shop, right, in the U.S., but actually it's the Salvation Army's motto, right? And so I think when you look at these complex textures, you can either be the pessimist here looking at the complexity that they give you, or you can be happy that these things now give you a whole new rich field to study full of donuts. Okay, so thank you. Oops. I don't know how that happened.
Thank you. And we just have a minute or two for quick questions just now before I hand over to the next speaker. Any questions for
I'll be here through this afternoon. Try the turkey.
You can ask Randall later on at coffee break and lunchtime if you have any questions.
Oh, it is.